Welcome back to this NPTEL online course in the molecular arrangement and reactive intermediates. In the last class, I talked about the hydrogen atom transfer. You have seen several different reaction where the hydrogen atom transfer is happening. So in the today's class, I am going to talk about the halogen atom transfer, and at the end, I am going to talk about some of the modern photoredox catalysis, how the catalyst can be used in the photochemistry to do a lot of the carbon-carbon bond forming reaction. Okay, and then most of the reaction you are going to see towards the end going to be the visible light photoredox catalysis. So let's start with the halogen atom transfer. So and then we are going to understand the mechanism, and then we are going to learn very briefly what is called the proton coupled electron transfer, and then I think the rest of the time I am going to talk about the visible light photocatalysis. As you can see from this from the term from the halogen atom transfer, we have seen some of the reaction that if you have a carbon halogen bond, you have seen in case of the samarium reaction, or you have seen for the tributyl teinhydride reaction, you have seen that what is happening, that is actually cleaving this carbon and the halogen bond to generate a radical species. So there are three different ways I have mentioned. It could be direct homolysis of this Rx in presence of the UV light. It can form the R dot or the X dot. It could be a single electron transfer. I think I am going to explain some of this in the the visible light photoredox catalysis. You are going to see that the catalyst can do a single electron transfer where it can able to cleave this bond again to form the R dot and the X minus. So it first the single electron transfer going to happen, and then it is going to form the R dot, or it can happen here that there is a halogen atom transfer. So what is happening here? You are actually, you can think about, you are giving another radical which is going to cleave this Rx bond. So which is going to take this X as a X dot, and then you are generating a R dot. So now you are forming the YX. I think the most important thing is, so so actually this reaction very much depend on what type of Y dot you are using, and what is the bond energy of Rx. Okay, so there are a couple of important factors which I am going to discuss. So first thing, we are trying to understand this this reaction, that once this bond is getting cleaving, it is forming some sort of a tangent state here, where you are seeing this bond formation is happening between X and Y, and there is a bond breakage happening, okay, in the tangent state, and then it is going to form the R dot and the the YX. So if you try to see about this reaction, then there is a tangent state here. So you start with this Rx and they end with the Y dot, and from there you are forming the product. Okay, so you can see clearly that this is a exothermic reaction. Your product is more stable than your starting material. As I mentioned, the bond dissociation energy is a very important factor here. So this is the important factor which we call as a enthalpic effect. This is depending on the bond strength. But then the stability of this tangent state, so depending on, you can see this energy going to get vary. So this is the effect. So this delta G depend on the polar effects, steric effects, and the hyperconjugation. So these are the factors which are going to stabilize this corresponding tangent state. Okay, so based on that we are going to see the different rate. So you are going to see the enthalpic effects, as I mentioned, the polar effects, hyperconjugating effects, the steric effects. So I am going to discuss very similar to the hydrogen atom transfer. I am going to discuss few example where these rates are measured. So as I mentioned, there is enthalpic effect. The bond dissociation energy is a very important parameters. Okay. So and then if you see the bond dissociation energy of the the YX which is forming here, okay, which is a if you see, once the YX is going to be the more stable, then the reaction will be in the forward direction. The stability of the R dot also is a very important factor here, and there will be polar effects. And then there is a important thing, that the nucleophilic character of the Y dot, because you will see the most of the time this Y dot which you are going to use for this type of ZAT or the halogen atom transfer, it is going to be a nucleophilic radical. Okay, because you can see the X dot which is going to form here, from here it is a electrophilic radical, and which together going to form this YX. So now you can see here the the cleavage of this, the phenyl and the X, this bond is getting cleaved here. We are using a nucleophilic radical here, the triethylsilyl radical. So you can see the there are different rate if you have this iodobenzene versus bromobenzene versus the chlorobenzene. and you can see this is completely depending on the the bond energy of the. So you can see once you go from the iodine to the bromo to chloro, the bond dissociation energy of this iodobenzene and chlorobenzene, you can see the bond dissociation energy getting decreased in this direction, and at the same time the Z reactivity getting increased in this direction as well. There is another example here. This alkyl radical is leaving this tarbutyl and the halogen. So the tarbutyl chloride versus tarbutyl iodide versus tarbutyl bromide, again you can see the Z is getting increased in this direction. Again there is an example here. Now I think the other important factor, as I mentioned, that the stability of these corresponding radicals which is forming here. So if you see here, there is a benzylic radical versus the tarbutyl radical, secondary radical, primary radical. So in this direction the radical stability is getting increased. Okay. So that's how you can see the rate is higher in this. So the Z rate is also higher in this direction. Then there are another interesting concept, that if you have alpha amino radical that can also able to participate in this reaction, or the alpha hydroxy radical, this can also because again they are the nucleophilic radical, they can participate in the halogen atom transfer to generate this radical species here, and then from there it can form this corresponding X, which can go to the corresponding iminium ion. Or here what is going to happen, it can convert to the corresponding carbonyl compound after the elimination. After you can see this comes back, get rid of the halogen to get to this carbonyl compound. So what we have learned, there are some polar effects. So we have learned that there has to be the nucleophilic radical like the tributyltene or the silyl, or you see this type of radical, alpha amino radical. And we have seen in case of the hydrogen atom transfer, so this is going to be electrophilic radical. You remember we talked about this in the last class, that there are so this is going to be electrophilic radical which is going to go for a hydrogen atom transfer. So that can able to clip this the carbon and the hydrogen bond to generate this R dot. Okay. And most of the times you end up seeing that these are the radicals which are forming here, they are actually nucleophilic in nature. So again there is a alkyl halide substitution pattern. You can see again, once you are forming this corresponding R dot from this species, what is happening, the stability also going to be make a difference. If you try to compare between them, what is the difference happening here? You have a 2 ester group which is stabilizing this radical more. So the radical stability will be more here compared to this. That's why it will be at least 10 times higher. So you can see here so this will be 10 times higher compared to the the other one, where you have only 1 ester with 2 methyl group. Very similar thing happen if you have a bromide also. Okay. So now we are going to talk about some of the application which I think we have already talked about in this reaction when I was talking about the intramolecular radical cyclization. But again you can see these are the very similar concept here. So there is in this particular reaction you are going to see there is the the halogen atom transfer and the hydrogen atom transfer, both are happening here. So now I think the first thing is, if you have the AIBN, if you remember I have already talked about AIBN, that once you heat up it is going to generate a more stable radical here. If you forgot about it, you generate this radical from AIBN. Now what is going to happen, that can able to have go for a hydrogen atom transfer, okay, from this. So that can go for a hydrogen atom transfer to generate this tene radical here, and once you have a tene radical, it is going for the the halogen atom transfer first to form this radical species, which can go for an intramolecular radical cyclization, and then it will form this radical here which will go for another intramolecular radical cyclization. So there is a 5-exoteric and 5-exodic to end up here, which can finally go for a. So you can see I already talked about the vinyl radical is a more reactive radical, so it will go for immediately hydrogen transfer to get to the product. So that is all about that. I think we can also practice some of the some more reaction during the assignment. Now I think I am going to briefly talk about what is called the proton couple electron transfer, and I will just talk about only one example about that. So you can see here what we are talking here. So we know about the electron transfer going to happen. We know about the electron going to transfer from the metal, or I think mostly we are going to see here. We are going to learn them there in case of the transition metal photoredox catalysis, there will be electron transfer going to happen. But here we are learning that there will be a proton couple electron transfer. So what is going to happen if you see about this particular example, that the carbon H or this if you have a carbonyl group here, especially we are talking about E equal to a oxygen. So in a carbonyl group, if you think about E equal to oxygen, what is happening in presence of a proton source, this oxygen is going to get protonated. So now you can, if you have seen that this reaction, what you have learned, the reduction of this carbonyl group highly dependent if you have the protonated form or you have a non-protonated form. Because once you have a protonated form, now the transition metal can able to, the transition metal, the photocatalyst now can able to go for electron transfer to form this species. Okay. So now you can able to the reduce the carbonyl group to make this radical species here. So what is happening, this proton which is getting coupled here, that is allowing the electron transfer to happen. So that is called the proton coupled electron transfer. So you can see a mechanism here, what is happening. So you actually form this carbonyl group under the photoredox catalyst and the Bronsted acid catalyst and the stoichiometric reductant. What they are doing, they are generating after the proton coupled electron transfer, they are generating this ketyl radical here. This ketyl radical can take part in a cycloaddition with the, it can take part in a 1,4 addition with these alpha beta unsaturated carbonyl compounds, and at the end, this after the addition going to happen, it can generate this radical here, and then at the end it will be finally this, it can able to go for a the hydrogen abstraction, and finally this OH and the ester going to get form this corresponding lactone. So this work was done by the Noel's group from the Princeton. They have shown that you can able to do this proton coupled electron transfer using a proton source, as I mentioned, a Bronsted acid catalyst and a photoredox catalyst can able to this radical species. So in this reaction, what they used this ruthenium bipyridyl complex, which we are going to explain in a minute. What is their structure, how the reaction happen from there. They use a HX source. So what is happening here, the ruthenium in the excited state going to what is going to happen, it is going to get to the excited state here. We are going to talk about this mechanism after a few slides. It is going to go for first, so there will be a electron transfer going to happen, and you can end up forming the ruthenium 1. In that stage, it is going to go for a proton coupled electron transfer here to generate this this species here. It can going to convert to the ruthenium 1 to the ruthenium 2 here. Now you can go for this, the ketyl radical cyclization going to happen first, and then there will be a hydrogen atom transfer, and then you can see now you have this ruthenium 2. So then there will be the ruthenium 2 again, what is going to happen, it can go to the corresponding excited states and start the process. Okay. So there will be electron transfer going to happen from here, and it is going to start the process. So now I am going to talk about, I think till now I think what I have talked about, the most of the reaction I am talking about UV light. You need a UV light starting from this several different type of reaction using tributyl hydride, using AIBN under heat, or you have seen a lot of reaction like Petrano-Bucci reaction or some other chemistry I talk about. I think the dipyrmethane rearrangement, most of the time I was talking about the UV light, because you have to understand, to go for this N to pi star transition, you have to use a somewhere in the 280 nanometers. If you want to pi star for a olefin, it is somewhere around 200 or 180. Okay. But now we are talking about a a photoredox catalyst. So how can you able to generate a radical species using a organo or using a transition metal based photocatalyst. So this will be a mild condition, user friendly, and of course the environment will begin. So again, I think we already learned about this, I have already shown you this diagram. I think you have seen there this N pi star pi star transition, mostly with the UV light. Now we are going to talk about a visible light here, which is starting from the 380 nanometer to 750 nanometer. Okay. So we are talking about the catalysis which are happening in this range. So there are different type of photoredox catalysts using the ruthenium or using iridium. So and also there are some of the the organophotocatalyst. We have shown some of the example here. There are more example of organophotocatalyst. So here I think the example you have shown, they are the donor acceptor photocatalyst. Again, I am not going to talk about more about these things in this particular class. So briefly going to talk about some of the important fact. So now if you try to understand about this particular complex, it's a it's a low spin complex here. Okay. So you can see here it has this T2Z with the D5 octahedral complex. So here you can see there will be a metal to ligand charge transfer going to happen. So once So once you shine light here, what is going to happen in under the, it's going to absorb the visible light, and there will be a metal to ligand charge transfer. Okay. So once it is going to the excited states, it is going to be excited state singlet, from there it is going to be excited state triplet. So now once it is in the excited state, it could be a a reductant or a oxidant. Okay. So it is absorbing in the 450 nanometer. Now you can see it is absorbing the visible light. There is a it's a long lived triplet state here. That means it is going to go to the singlet to the triplet state, and from there it can go for electron transfer or it can go for energy transfer. So and then it can go for the single electron transfer. And again, as I mentioned, it could be effective oxidant or reductant. Now if you see about this diagram, what we are trying to show you, this is the metal T2G. From here once you shine light through the metal to ligand transfer, what is going to happen? It is going to go to the pi star orbital of the ligand. So metal to ligand transfer going to happen in the excited states. So first there will be metal to ligand transfer, then there will be intersystem crossing. So it is going to generate a triplet state. Now it can be a very good oxidant or very good reductant. So based on this redox potential, you can see it can able to go for oxidation of some bonds, or it can go for it can able to act as an oxidant. So that means it can take a electron from somewhere, okay, or it can able to it can act as a reductant. So now you can see here we are trying to show you, it is going to absorb the visible light, go to the singlet excited states, there will be intersystem crossing to the triplet excited state. From there it can be a very good oxidant or very good reductant, and that also depend on what type of things you have. You have to match with the redox potential. Okay, that is the important factor here. So depending on the redox potential of your excited photocatalyst, it can be oxidant and the reductant, and of course depending on the substrates. So that is all about the the electron transfer, and there is another thing happening called the the energy transfer. That means in the excited state, excited triplet state, it can also act as a energy transfer agent. So it can transfer the energy and come back to the ground state from the excited triplet state. So there it can transfer the energy to the substrates which cannot be excited, and then the substrates can go to the excited state. From there it can able to participate in different type of reaction. It can go for isomerization, and it can go for some sort of a +2 reactions, and some other chemistry can happen from there. Okay. So again there are this energy transfer can be a Foster and Dexter. Again I think we don't have to discuss more detail here. So this is a very general things I just want to tell you about this visible light photocatalyst. I just want to show you two important reaction which was discovered in the 1970s. One of the reactions of about this Kellogg reductive desulfurization. What is happening here, if you see we have learned about some of the reaction here in the under the UV light, where if you have this carbon bromine bond here instead of the sulfur, under UV light you have seen that it is going to form the the radical, and then it is going to get a hydrogen atom abstraction. But now we are using a visible light using this ruthenium catalyst. So what is going to happen once we excite the ruthenium catalyst, it is going to go to the excited state. So first thing, it is going to go for you can see here it is going to go for a electron transfer going to happen from here. From there it is going to form the ruthenium +1, and now what is going to happen, now this stage the ruthenium +1 want to go to the ruthenium +2. So it is going to what is going to give, it is going to transfer one electron here. Once it is going to transfer one electron here, this bond going to get clipped, and you see this is getting out, and it is generating this radical. It's alpha keto radical generating happen. And once it is generation happening, this radical is just stable radical. We have learned it can go for a hydrogen atom abstraction. So this hydrogen atom abstraction going to happen, this is going to form the product. And then the other important reaction which was discovered in the 1980s. So here you have a diazo compound here. We already talk about how you make this compound from the aniline. Now using the the ruthenium photocatalyst, you can able to convert this to the corresponding H here, and at the same time you can see here you end up making a phenanthrene. Okay. So starting from this isolated phenyl ring, at the end you are making some sort of a cyclic product. So we will quickly learn about the mechanism, what is happening. Again the ruthenium in the excited states, what is happening. First it is going to as you see the ruthenium 2 to the ruthenium 3 happening. So it is going to, as you have learned, I think in the copper chemistry we have already talked about the Sandmeyer reaction. You have seen how it is generating aryl radical here. Very similar thing happening here. So ruthenium is giving one electron here. That way it is going to get as a N2 out, and a phenyl radical formation happening. Now this phenyl radical is coming in and it is going to add to this aromatic ring here. Generation of this radical, further the ruthenium will now take back the electron that will generate a positive charge here, which will go for a hydrogen abstraction, which will go for a proton going to take from here, and the, that is going to form the corresponding phenyl 3. So in this particular topic, I talk about the halogen atom transfer reaction and its reactivity. I talk about the different factor, how it is important in the halogen atom transfer reaction. I also talk about how the bond dissociation energy is very important for, and also you have seen that there are some other factors that like that you have to use a nucleophilic radical for this reaction. Okay, and then you have seen that how these reactions are important once you are using the alpha radical for this reaction. And then at the end I talk about what is the definition of the proton coupled electron transfer. I think I have shown you one mechanism how the proton is binding with the oxygen, so that is allowing to the reduction of the carbonyl group to generate a ketal radical. And then I talk about the visible light photocatalysis, how different from the UV light. So now you are using a photocatalysis which can act as a catalyst in the reaction. It can absorb light in the visible range. It can go to the excited singlet through intersystem crossing to the triplet. From there it can go for a single electron transfer or it can go for energy transfer. And we have seen some of the example for this reaction as well. And again these are the references here. And again thank you for coming to the class, and I am going to see you guys in the next class. Thank you.